we are going to start the path integration part 4. The last 3 parts, excuse me, were all on quantum mechanics. The first one was introducing some of the notation. The second one was defining new concepts like time ordering and functional derivatives. And then this last one, last week, was the harmonic oscillator. And the harmonic oscillator using Fock space, F-O-C-K space. And then we did kind of some interesting things with that. And now this week we're going to take something and kind of parallel it to that harmonic oscillator. So let's see where we got to last week. So path integration, part 4. Now the only reason, for those of you who are new, the reason that we do path integration is because people asked. Someone said, hey, I'd like to learn path integration. And I said, hey, I could use more learning path integration myself. How about I teach everybody? And then enough of you said, yes, please do that. So I chose to do it. Now, very soon in the next few weeks, I will be adding another one of these sessions to Friday. And what I was told is tensor analysis, which would be very helpful for me to learn. So if anybody's interested in tensor analysis, please continue to let me know. So where do we leave off? Well, we were talking about the harmonic oscillator. We were talking about the harmonic oscillator in Fock space. And we ultimately got down to finding the amplitude to starting in the ground state and ending in the ground state was dependent on RF, our source. The external source that was causing some sort of change to the system, right? Whether it be interaction or potential or whatever, didn't matter. It was causing some sort of change. So we got to this integral right here with dt prime, f of t, g of t minus t prime, and f of t prime. I will say this, if anybody wants to come back for the meme review, or the meme react, we'll probably be doing that around 4:15, 4:30. So feel free to, if you guys are not interested in the path integration, you can always come back in about an hour or a little bit less. Now we want to move on to quantum field theory. This is where we got last week. We had the amplitude from the ground, from the zero to zero, from the ground state to ground state. And here we got like our source function, our Green's function, and our source function. Now, these, again, we had more terms in this, but we realized that they canceled out in the vacuum energy. It was basically the same thing as starting in the 0 and ending in the 0 and doing nothing in the between. And remember, these are paths. We're trying to do path integration. So doing nothing from 0 to 0 makes no paths. So we are able to cancel that away, and then the only other thing is summing over all of the other paths that could possibly be made. Now, remember, well, we'll get to it in a second. Let's talk about quantum field theory. We're done with quantum mechanics. We are now on to quantum field theory. So let's kind of draw up a different Hamiltonian. Before we saw the Hamiltonians as, well, we saw like the Hamiltonian for the harmonic oscillator. But now let's come up with a different one, and then I'll explain where it comes from later. But we can do this Hamiltonian, which is basically the Hamiltonian for a free field where we have some kinetic term plus some potential term. And what happened here? Oh, the song ended. That's weird. I feel like that ended really abruptly. Now, so what do we do with this? Well, let's take a few things and kind of identify them. This is just going to be the momentum terms that we're going to end up kind of like getting rid of. And I'm going to kind of get rid of these the same way that we got rid of the momentum terms before. So don't really worry about what this is. But here we have like the change in the phi, where the phi is the field, and then the mass squared times phi squared. Now, let's do a little bit of things that we did before. Last week we had a lot of q's for position. So now we're going to take that q and then we're going to send it to a field. Oops, wrong Greek letter. The field being this phi of x and t. Okay. Now we also had like the operator q, which this one we're also going to include it into the the phi x of t. And the way that Shred-Nicky does this, the book that we're following is Shred-Nicky. The way that Shred-Nicky does this is he just says that it's going to be obvious which one's going to be quantum and which one's going to be classical. So we're just going to say, for the sake of argument, that if we're going to talk about operators, then we'll know whether or not it's quantum or classical. And it's mostly going to be quantum because we're going to be talking a lot in like the Fock space and the ladder operations. But I think the most important one is that the source term is now going to be modeled as J. And that's kind of like a very important thing for us, is to model the source term as J. Because remember, the source term is the thing that's going to go into the amplitude itself. Now, what we can do with this is if we take our old formalism, remember our old formalism.
It's trivial to see.
Now, what we're going to do is we're going to do the same thing we did before, where we go from the Hamiltonian notation with momentum and position, and this position is given by the field. We're going to go into the Lagrangian formalism. Now, this is going to be the big one. This is something I want you guys to remember kind of frequently. This is going to be the path. This is what's known as the path integral, or the functional integral, more or less. And that's going to be given by 0, 0, the ground state to the ground state with our source, and then going to be the integral over all of the fields, e to the I integral of d4x times our Lagrangian plus the source term. Now, this is going to be the thing that we've seen so many times before, right? Where we have the action plus some other thing. Well, this was our new adjusted. This was our new adjusted Hamiltonian, or Lagrangian for this matter, because we're doing the Lagrangian formalism. And we have that source term. So now let's talk about what the Lagrangian actually looks like. And we can see through the formalism and getting rid of the momentum and everything like that, that this is really what we're going to do. Now, if you have done any quantum field theory, most of the things that you see...
Derivation of this proposition is left as an exercise to the reader.
Stop saying that. We did this. We did this last week. If you guys would like to see that, we can do it again. But that is something I'm going to actually have to prepare. But it's the way of going from the classical mechanics to, or I'm sorry, in classical mechanics is the formalism from going from the Hamiltonian to the Lagrangian. That's what this is. So we're doing that again, where we do the Hamiltonian to the Lagrangian. You get the equations of motion, you solve for the momentum, and then you plug the momentum back into the Hamiltonian, and then you let the Hamiltonian equal the negative Lagrangian. You get rid of the momentum as long as the momentum is quadratic, and that there's no p times q terms, and then you're left in just the Lagrangian, which is just in terms of q, or in our terms is now in terms of phi, the field. And then of course we have the integral over all possible paths, and I think this is what we need to. I guess I'll write proportional too. Proportional because we added some constants in there at some point as well. Usually the Gaussian constant from that e to the momentum squared gets tossed into this one as well. And what does this mean? Well, I think this is kind of like the most important part, right? This is not a sub x. This is a variable x. What is this supposed to mean? Well, this is the kind of the clincher, and I put it on. This is kind of the clincher, and I put it on Twitter because of how important it is to understanding path integration at this level. Okay, and I think that that this is something that took me a really long time to understand the concept of mathematically, and once I understood it, I kind of understood what we're doing here. Okay, so here's the concept mathematically. Okay, note, and this is straight from Shred-Nicky. This is a quote from Shred-Nicky that is really, really important, and it happens right after you introduce this integral over all paths. Okay, Note that when we say path integral, this guy right here, we say, we now mean a path in the space of field configurations. So what does that mean exactly? The path of field configurations is basically asking you, how can one particle get from one configuration to another configuration? How can it have one spin and go to another spin? How can it have one particle and go to another particle? I.e., like, say, like if we're doing Yukawa and QED or whatever, and you wanted to do electron to photon, like how could you have an electron and a positron and go to a photon? Well, there's all sorts of possible ways to get from that, from one configuration to another configuration, and then you're going to end up with all sorts of, how can you get from positron electron to positron electron? Well, you're going to have loop diagrams, and you're going to have all this other, and tree diagrams, you're going to have all these other different diagrams, but each of them has a amplitude, a probability amplitude, and that's what we're integrating over. We're integrating over all possible field configurations from start to finish. Those are the paths that we're talking about. It's easy to think about these paths as being trajectories, because that's kind of what we start with when we start with Qs. But again, like, once you get into, what's the two vertical lines? Oh, here? That's, this is just a capital pi, right? Capital pi? Is that what that is? This is product over all x's. So it's just going to be like d phi x1 times d phi x2, etc., etc. And is that capital pi? Is that what that is? Like sigma stands for fun, yeah, or for sum, yeah. So that's what this one is. This one's just a variable. I think it's the momentum term. Nikki introduces it without ever talking about it, and I think it's just the momentum term. Let's well, we're gonna erase anyways. But yes, that's where we're at.
It stands for fun too.
Yes, capital pi. That's what I thought. Alex Orio, thank you for the follow. Welcome, welcome. We are in the middle of some path integration fun. Okay, so let's be on the same page when we're talking about this amplitude is going from, or this amplitude more or less, is going from how many configurations of a particle or of a field, because now we're in fields, can we go through to get from the ground state of that field back to the ground state of that field. And we're going to get different amplitude for each configuration. Okay. Now today I want it to be a little different, because if anybody has any questions after we're done with this, I want to be able to answer them, and I will struggle through whatever answers I can.
I just won $48.80 playing poker.
Nice. What do you think the probability of that is? Sick. All right. Now, let's do, I dropped my chalk. So sad. So now we're going to go ahead and follow the same procedure as we did for the harmonic oscillator in order to evaluate z sub 0j, this path integral. That's the goal. We want to evaluate this. So as always, we have a goal. And then let's be a little bit more clean about the goal and say, let's evaluate z sub 0. Okay, of j. Now, we're going to parallel that with the way we solved the harmonic oscillator. How did we start by that? Let's do the same thing we did last time, a Fourier transform, right? So let's write down our Fourier variables. And we have, oh, it's supposed to be phi, not psi. I keep doing psi, why? A phi squiggle of k, where k is just some variable, is equal to the integral of d4x, because now we want to include special relativity in this, of e to the negative I k x phi x, and then what's our other variable? It's going to be phi of x equals integral d for k over 2 pi to the 4th e to the I k x squiggle phi of k. Whew. Okay, there's our Fourier transform. Not too bad. Of k. Okay. Now what's k? Well, I'm gonna tell you what k is. K times x is going to be equal to negative k, the time component. So k0 times t plus the 3 vector of k and the 3 vector of x. What's the thing above the d? This? I don't see anything above the d. d4k. Hi, how are you? So d4k is an integral in 4 space. So it's going to be like if you're integrating over all of the variables. So there's 1 for time, and then there's 3 for space, and we're integrating over all of them. That's the d4k. Good question. Very good question. So now let's isolate the action S sub 0, and let's talk about what the action is. So before it was before the Fourier transform, and again, just like we did last week, we isolated the action. And then we did a bunch of stuff to it. So let's redo that stuff. So we're gonna, so that's what we have for the action. Then let's do the Fourier transform. And what are we gonna get? So then we do the transform, and what are we gonna get? We're gonna get a new action that is 1/2 times the integral of d4k over 2 pi to the 4th times minus squiggly phi times k squared plus m squared. And probably the best way to think of squiggly phi is like it's a field, but it's in the coordinates of our new k, and that's just what the k is. And again, we're doing this simply because, well, it's a Fourier transformation, so we can do it as long as it's a legitimate transformation, which this one is. So then, well, we can just plus j squiggly k, phi squiggly minus k, plus j squiggly minus k, and phi squiggly k. So again, just like last week, we have our Fourier transform, we get something that looks like this, and then we get our 2 source terms multiplied by our fields. So what's k squared then, if this is k? Well, k squared is just going to be it's a 4 vector squared, so it's going to look like this. The 3 vector squared minus k0 squared. And now what do we do? Well, it's just that's what the k looks like. So if you're worried about what the k is, now you know in terms of the 4 vector. Okay. So what do we do with the what did we do last time? Well, when we got to this point, we did a u substitution. Good old u substitution, right? So we have this new variable, like fancy x, equals squiggly phi of k minus squiggly j of k divided by k squared plus m squared. And now what's nice about that is the sum over all of the squiggly x, or fancy x, excuse me, is equal to the integral, I said integral, sum. Integral over all, the fancy x is equal to the integral over all phi's. Okay? Now, once we make this u substitution, the action then takes on the following shape. Now this is, again, the second time that we're seeing this. So if anybody's struggling to follow some of these steps, then I highly suggest you go back and watch last week's video, Path Integration Part 3, and where we do these steps for a simpler case. This one's a little bit more complicated, but the steps are in fact the same. So we'll have squiggly j times k, squiggly j times minus k, all divided by k squared plus m squared. Oh, and then we have another term here. Minus, let's do minus down here, minus squiggly x, fancy x, excuse me, k squared plus m squared, and then fancy x of minus k. And then I think we have to close brackets, which I don't have in my notes. Okay. So, just as we did for the harmonic oscillator, we want to kind of figure out what the boundary is. So let's take our path integral, but now let's evaluate the source at 0, i.e. there's no external sources. Then what are we going to get? Well, we'll get that when j is equal to 0, we'll get the amplitude is 1, and this is what I was talking about before, about how we're not letting anything happen in between. We're saying we're starting at the ground state, we're ending at the ground state, and there's no change in the configuration states, right? Nothing is happening to the ground state. It starts in 0, it ends in 0. And if there's nothing happening to the outside, if there's no sources, there's no impact on the free field, then clearly, what's the probability that we'll get that? Well, it's going to be 1, okay? Because there's nothing influencing it. But that's no good. We know we have these source terms. We want to kind of figure out, this is supposed to be an S. I don't know why it looks like an integral, but there we go. We know we can evaluate the source terms. This doesn't really mean anything to us because we know that things change. Things don't always remain as free fields. So we need to evaluate what that change looks like. So let's go back and take a look at what happens when we don't plug in 0. And we know that like this is the thing that kind of stays when j equals to 0. So this is the thing we're going to have to ignore to figure out what happens when j does not equal 0. And the way that we do that is find the path integral now, which is going to be equal to, and again, we're going to ignore the second part because we know it's not going to contribute.
It kinda just sits there.
Was that for me? I'm not really sure. Yeah, it kind of just sits there. I think if you're talking about this, then yes, it kind of just sits there. But now let's kind of evaluate the thing that's actually getting adjusted, or it's influencing the actual particle. I over 2, so that it's the exponent I over 2 with the integral of d4k over 2 pi to the 4th. I should have set that equal to 1. Should have set that equal to 1, but you know, I'm getting more lazy in my old age, keeping on terms that aren't helping. K squared plus m squared minus I epsilon. All right. Now, this is the term that we kind of need to look at. What do we do? Well, we're going to un-Fourier transform it, right? Un-Fourier transforming it is going to get us back into the x. And now that we know we don't really have to deal with this anymore, we're just going to let it be. Then we can go ahead and figure out what the un-Fourier transformed looks like. So we're going to, I shouldn't say un-Fourier transform. I'm going to say we're going to re-Fourier transform it using our same things right here. So what is it going to look like? Let's go ahead and write it down. And then this is going to be right when we're going to get back to the same spot that we ended last week. We got a couple more things to say about it, but not too much. Today's lesson is going to go kind of quick. Again, hopefully we'll have some questions to talk about. But then what does the next one actually equal? Well, the next step of Fourier transforming it again back into this right here is, well, I guess we'd make this substitution, but you get the picture. The exponent of I over 2 times the integral of d4x prime, our source term, and then just like last time where we had that Green's function, now we have this guy right here, which is the propagator. Oh, and I have another source term. Oh, I wrote the source term. What am I missing? Just a bracket, I guess. Okay, cool. Now, the propagator, of course, if you were to go and actually look at what it looks like, the propagator looks like the following. Now, I plugged this in, but you know we want to know what the structure of it looks like. d4k, 2 pi to the 4th, e to the I, k, x minus x prime, divided by k squared plus m squared minus I epsilon. Okay. Bring Soda, welcome, welcome. Thank you for the follow. Welcome to the channel. Okay, now, so we have here the path integral, the thing that we need, the thing that's going to be influenced by this, or influencing our free fields, the sources, which are jx prime, the actual things that are influencing the sources. And then we have, in the middle, we have this propagator, basically telling us what's going on from one to the other. And that's given by this, which we have seen now a bunch of times and will be very relevant in the next few steps, because the Feynman propagator is a very specific Green's function for the Klien-Gordon equation. Thank you for the redemption of the hydrate. That's officially referred to as the inverse it might. I actually don't know. I just know it's just doing the Fourier transform again. But maybe it's inverse. I'm not sure. But I don't know what the specificity of it is. Oh, sweet. I have another hibiscus. Okay. Now, thank you for that reminder to hydrate. I need my notes, not the towel. So we know that this is a specific Green's function, and for the one that we need it to be, it's the Green's function for the Klien-Gordon equation, right? The free field. So here's the Klien-Gordon equation. You have some derivative squared plus m squared times our propagator, which is equal to our Dirac delta function. Now I have a whole video, a whole VOD in Twitch. It's not on YouTube because people didn't show any interest in me turning it into a YouTube video. But it is a VOD in down below, and it has the Green's function seen from just this point of view, right? This quantum field theory point of view. We know what the Green's function is because it solves equations of symmetry, like the Klien-Gordon equation. And in that video, I kind of did it more like a canonical, where I just sort of made the transformation into a propagator from a Green's function. But now we can actually see a very specific solution, which is a special case of Green's function that solves the Klien-Gordon equation. I don't think I did the Klien-Gordon equation. I think I did a different one on the actual Green's video. So if you want to see something different, I think I did the Dirac field. But let me just say one statement about this that's in Shred-Nicky that I didn't have time to do, or I just didn't do it. I probably had time. I just didn't want to do it. I don't know the residue theory very well, and I definitely don't know what was the second part of that? Bessel functions that well. But Shred-Nicky does say that you don't necessarily need to do this way to find the propagator. You can treat, and I'll just tell you exactly what he says. You can treat the k sub 0, the time component of the k vector, as a contour integral, and in the complex plane, in the complex k plane. And then you can use a combination of the residue theory as well as the Bessel functions to come to this conclusion. But I did not do that. If anybody does do that, let me see, because I'd be interested. But my Bessel function is not strong. I got no Bessel game. Okay? I got no Bessel game. But I would be interested in seeing that if anybody does do that. And maybe someday we'll do that for stream. Oh, okay. I see, Pretz. Yeah, I just know that we're doing a Fourier transform again. Okay. So, let's see here. So now, where do we go from here? Where's the final few steps of today's lesson? Today's lesson's pretty short. I probably could have kept going. Well, no, because we're going to do questions. There will be questions. We can do the time ordering, right? And that's ultimately what we need to know. We'll have some time ordering operator of all of the fields. And we need to kind of understand what that means, right? Well, we already did establish that this is, you know, a product of all of the interesting functional derivatives. Like after a while, we know using perturbation theory that we're going to get terms that aren't going to contribute enough to care. So we can figure out how many terms we want to care, and we can do that very nicely using path integration. So for instance, let's take another example. And again, this is going to look exactly like last week because we are literally paralleling this to the harmonic oscillator. If we wanted to know how many configurations between a field at x1 and x2, you know, we can figure not how many configurations, but the probability of a specific configuration from x1 to x2. How can we do that? Well, let's apply all of the functionals that we need. How many functionals do you think we'll need? Yeah, we need 2 functionals. I actually miswrote this. This is supposed to be down here. So let me fix that in case anybody is not following along in my notes. It's supposed to be how many ever functions you need. And now for this one specifically, we just need 2 functional derivatives. And that is 1 over I, the functional derivative, j of x2. And that's z sub 0 j. Evaluated j equals 0. Okay. Now, applying the functional derivative to our path integral, what's going to happen? Well, remember, this is our functional derivative, or this is our Green's function. This is our functional derivative right here. It's an exponent. So if we apply the first one in terms of jx squared, then what's going to happen? Well, we'll end up getting, or jx2, excuse me, not jx squared. jx2 will end up getting 1 over I times the functional derivative of jx1 times, and remember we're applying the functional derivative of jx2, so applying the functional derivative of jx2, you get the jx down, you get the derivative, or the blah blah blah, the Dirac function, and what are you going to actually get? You'll get the integral, I know I said a lot of garbage there, just ignore it, d for x prime times the Green's function, or the propagator, but now instead of x1 to x, or x2 to x1, it's x2 to x prime. And then our source term gx, or yeah, jx prime. This is not too complicated of a derivative and integral to do. If anybody wants the outline of the process, one thing you would do is when you take the derivative, the functional derivative of this, it's an exponent, right? So you're going to take the derivative of this whole thing, and then the derivative of the top, right? And the derivative of the whole thing is just going to be the whole thing again. And then the derivative of the top is going to be, you're applying this j, it's going to hit this one, and it's going to be evaluated like a Dirac delta function would be evaluated, because you're going to get the Dirac delta function inside this, right? And from that, you'll end up taking down one of these source terms. That's why it's gone from here, right? You'll take down one source term, and then you're going to evaluate this function as, because of the way that the Dirac delta works, you're going to replace the variable here with the variable in the bottom of the functional derivative. Okay, that's why the x2 moves to inside the Dirac delta function, or the propagator, and then this one doesn't. But you can see that we're going to do the same thing, and we're going to get the exact same result. We're going to apply it. Am I dropping Oh no, the z is right there. Okay, so we're going to apply it again, and this is what we're going to get. We're going to get 1 over I times the propagator of x2 minus x1. It's a fun little derivative and integral if you guys want to do it. It's not too difficult. And then we're going to say higher order terms of j times z. And I just say higher order terms because if anything has a j in it, then at this point we can just set j equals to 0, and it will go away. So really, we can talk about this propagator, again, following this form, which is the amplitude that you're going to get from evaluating this amplitude right here, right? We did the same thing at the very, very first time we talked about path integration, right? We wanted to know what it was like to go from one state to another state. We brought everything inside. We took care of the time ordering operator, and we got this nice formula. And then we were like, what do we do with this nice formula? Well, then we did all the solving, and now we have it. So if you're talking about going from one state, one configuration state, to another configuration state, what's this amplitude right here? And it's going to be given by the propagator right here, where x2 and x1 can be evaluated in that sense. I always loved this functional derivative approach. First learned it from Raymond, Field Theory of Modern Primer. Awesome. Really makes a compact way to get the Feynman diagrams quickly. It really does. And I think like a lot of the things that I was stuck on when I was learning this was not being able to evaluate this derivative and this integral, the integral you get from the Dirac delta. I highly suggest if anybody's serious about trying to learn this stuff, really work on that, because that's a fun exercise. It's really a lot of fun to take that derivative and then do the integral properly, the delta integral. And then do it enough and you get this beautiful propagator that gives you the amplitude to go from one state to another state. Now, there will be more, but like we could do this again for multiple states. So I think we're all good with this. So let's do a couple. Let's do one more. I don't think I did this. I think I did this last week, but it's literally, again, I keep saying this, but it's true. This is a parallel to the harmonic oscillator. So we're not doing anything crazy new or interesting. We're just showing exactly how the harmonic oscillator works as a great model for understanding particle physics.
If you go from one state to another, you might need to quarantine.
Thank you very much. It's very good. So if we start at the 0 state, and now let's consider a bunch of particles, right? What's the possibility from getting from x1, x2, the configuration states to go from x1 to x2 to x3 to x4? Like, what is the possibility to get from, for these 4 particles? Because remember, you're not going to be able to stick multiple particles in these outer states. So say if you wanted to go from 1 to 4, or from 1, 2 to 3, 4, something like that. I guess you could do outer. I guess like in the first lesson, as we saw, you could do multiple particles. Diadacokinetic. Welcome. I don't know if I got that right, but if I did, wonderful. If I didn't, correct me, please. Welcome. Thank you for the follow. Doesn't know anything about to do with path integration. Oh, stop. No, not dumb. He's great at programming.
Who needs church every Sunday? We should do quantum physics every Sunday with Eric.
Okay, so so say we're trying to figure out how to go from 2 particles, to 2 particles out here, right? How are we going to do that? How are we going to go from this particle to this part, to this? What's the possibility? So we can put everything, we can cram it all on the inside and start from the ground states. Like we did that. We talked about that the first week. We can do all of that. And then what do? Well, now we have a nice prescription for handling this. And if we do all of the path integrals, which can be a bit hairy, but we can generalize it now, we'll get the following. The propagator from x1 to x2 times the propagator from x3 to x4 plus the propagator from x1 to x3 times the propagator from x2 to to x4 plus the propagator from x1 to x4 times the propagator from x2 to x3. Now, what does this mean with our graph? Well, if we have 2 particles in and 2 particles out, then there's only a few configurations we can think about. But it's going to be all of the pairs, right? We can go from 1 to 2, so it's going to be like this. 1 to 2, 3 to 4. So we'll say 1, 2, 3, 4. We could go from 1, 2, 3, 4. We could go from 1 to 4 and 2 to 3. And lastly, we can do 1 to 3 and 2 to 4. 1 to 3, 2 to 4. So these are all of the different options, and each of those carries an amplitude with it, right? Each of these configurations carries some probability amplitude that you're going to see this happen, or that this is going to be the actual case that you'll get. And so this is all what we've done here. Now we can break this up into 3 pieces and evaluate each amplitude of one of these possibilities happen. Or we could just say, if you want to get from 1 to, from 2 in, 2 out, what does that look like? Well, you got all of those configurations to think about. Just say kinetic, most streamers can't say. Fair enough, kinetic. Thank you, and welcome. Okay. Alrighty, what do we got? Oh, so let's just start down the general formula, okay? And for our canonical friends, this is where we do that meme where we're like grab arms and like shake it, the path integration friend and the canonical friend, because this is where we all converge. If you go from the state from x1 to x2n to n, then we can get the following. We can get 1 over I to the n times the sum over all pairs or pairings of propagators. So we'll say x to the I1 minus x to the I2 dot 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 dot, and then the propagator last one's going to be I2 to the n minus 1 x minus xi 2 to the n. And every single one of these propagators is going to be another version of this. So like for us, it's easy with 4 fields. For us, it's easy with 4 fields, but you can considerably do it with any number of fields. And yes, these are ridiculously long calculations. They take a lot of time to get through them all. But here's where my canonical and friends and I... Hi, Lord Lycan, how are you? I don't know what that means, but it's kind of funny. And here's where my canonical friends and I, we converge, this is also known as Wick's theorem. And there's another way to get to Wick's theorem, which is the canonical formalism. So in my research, we are rewriting all of this using a different statistics. And different things happen, like in parastatistics. Like for 4 fields, you're not going to get all of these. You get something different. And it has different consequences and things like that. But he does the canonical version of this to get to Wick's theorem, and I do the path integration because his canonical formalism, or I don't really know the canonical formalism for us. It's really rewriting a lot of formalism because the canonical formalism is a lot more ad hoc than the path integration. Path integration is much more detailed and like step by step. So I'm using all of the same formalism to get to the conclusion. But for the canonical formalism, we have to actually rewrite a bunch of formalism, which is really, really, really extensive. John Wicks. For our canonical friends, thanks for making such a great opera. All right, now I said I would do it. It's been about 45 minutes. I finished the material. Does anybody have any question? I still have zero idea what all these symbols mean, but I like how passionate you are. Awesome. You mean the sum over a path distance? No, that's the point that I was trying to really, really iterate, is these are not distances. These are configurations. So like, for instance, what's a good configuration? How about, Well, we could talk about spin. Think about the spin of a particle, right? We know enough about the spin of a particle to know that it behaves just like spin, and it is in fact not actually spin. It's more of like a set of, it's more like a number that is associated with a particle. So a particle has spin up, right? Now, we want this to be the beginning state, and we want this to be the end state, right? Spin down to be the end state. Well, how many different possibilities can we go to get from up to down? Well, we could have, spin up to spin up to spin up to spin down. We could have spin up to spin down to spin up to spin down. We could just have spin up to spin down. Like, we can have all sorts of possibilities. Like, every single path to get from spin up to spin down has to be considered, right? That's what path integration is. It's considering every single possibility that the particle could be from here to here, right? And when this is a free particle, we know it's not going to change. It's not going to interact. It's not going to decay. It's not going to scatter. It's not going to turn from an electron into a photon. This is just a free particle, but it's still experiencing something, right? And that is just that it's propagating from one spot to the other. This is literally, where is it? These are all 4 free particles. So they are just going to be traveling from one spot to another. That's the propagator. It's propagating through space, one spot to another. So how can it possibly propagate through space? Well, there's 3 different ways that these particles can propagate through space. So now that's a configuration of just propagating, where this is, again, not propagating like a trajectory. This is saying it's starting one way and finishing one way, just like the spin states. It's starting spin up and it's ending spin down. How it gets there is a whole different beast. Is there any other questions, or are you guys comfortable with just, with continuing going? Next week, we're going to be doing interacting fields. So we're actually going to see particles start to change via an interaction Lagrangian.